Unsupervised learning algorithms. Okay, today we are going to see this unsupervised learning algorithm. In unsupervised learning algorithm, when we compare it with the supervised learning algorithms, there is no clear distinction between these two. Okay, the distinction between the supervised and unsupervised algorithm is not formally and rigidly defined because there is no objective test for distinguishing whether a value is a feature or a target provided by the supervisor. Okay, so we cannot actually clearly distinguish this supervised and unsupervised learning algorithms. The supervised learning refers to most attempts to extract information from a distribution that do not require human labor or labor to annotate the examples. So generally when we say about supervised learning, we talk about the input-output pair. So we give the labeled data, and based on the labeled data, we can train the system. And after training, if we give any unlabeled data, it will give you the proper output. That is in supervised learning. And when we talk about unsupervised learning, we say that we give unlabeled data to the system, and the system itself identifies the data, or it categorizes the data. Okay. So that is unsupervised. So a classic unsupervised learning task is to find the best representation of data. Okay, that is okay. So that is the best representation of the data. So maybe it may be the clustering problem, or it may be the PCA, that is component dimensionality reduction, or those things. So anyway, this is called the best representation of the data. We will come to the examples later. And when we consider the unsupervised learning algorithms, some of the algorithms I have listed here. One is principal component analysis. Principal component analysis, or PCA. Then second one is K-means clustering and hierarchical clustering. Okay. So we are going to discuss this principal component analysis and K-means clustering in this lecture. And principal component analysis, or PCA. So what is it actually means? It is basically used for the dimensionality reduction. Dimensionality reduction means we have assume you have a 3 by 3 matrix. Okay, you have a 3 by 3 matrix. That means you have 3 columns, and you want to reduce this 3 by 3 matrix to a 3 by 2 matrix. You reduce the column by 1. Okay, instead of 3 columns, you need to take only 2 columns. So that is actually dimensionality reduction. And in doing this dimensionality reduction, we require a principal component analysis. That means if I am cutting down one column from these 3 columns, I have to identify which are the most important 2 columns. So that I can cut down that least important column. Okay, so that is principal component analysis is all about. Principal component analysis, or PCA, is widely used technique for dimensionality reduction of the large data set. Okay, so you think about a data set which has 1,000 columns. Okay, 1,000 features are there in the data set. You have 1,000 columns in a table. So in that 1,000 columns, maybe only some 800 columns are relevant, and the other 200 columns are not relevant. So we need not require that much computational power to process all the 1,000 columns. So instead, we can remove these the 200 columns, so that we can utilize our processing power to process the remaining 800 columns. Okay, so the data that we have to handle, that will reduce much when we reduce the dimensionality. The principal component analysis algorithm provides a means of compressing data. So we can say like that. That means we compress the data from 1000 to 800. Okay, there is a reduction or compression. We can also view PCA as an unsupervised learning algorithm that learns of data. So I represented the data in 1000 columns, and I am going to find a new representation of these data with the 800 columns. Okay, so from 1000 to 800 there is a reduction. So it's a different representation as well. Actually, we are not simply cutting down the 200 columns. Okay, that also we should understand. That means the data there in those 200 columns, uh, its effect should be there in the remaining 800 columns. Okay, we cannot simply cut down those 200 columns. So that is the importance of this technique. Where the effect of those 200 columns data, that effect should be reflected in the remaining 800 columns. Okay, that's what we have to do. The PCA learns a representation that has a lower dimensionality than the original input. Okay, that's what we said. Original dimensionality was 1000 and we reduce it to 800. Okay, for example. Then reducing the number of components or features cost some accuracy, and on the other hand, it makes the large dataset simpler, easy to explore and visualize. That is the advantage. So if you reduce the if we reduce the dimensionality, there we have to compromise on accuracy. I mean, a minute point accuracy compromise may be there, but at the same time, on the other side, we make the data more simpler, and it makes it easy to explore the data and to visualize. Suppose you visualize a data in 4D, that is very difficult to visualize 4D data, and if you convert it into three-dimensional, it is very easy for the audience as well as the developer. Okay, that is the kind of thing. It is easy to visualize. If the dimension is reduced, it is easy to visualize. Also, it reduces the computational complexity of the model, which makes machine learning algorithms run faster. Okay, so when the complexity reduces, the algorithm will work well. Then the PCA also learns a representation whose elements have no linear correlation with each other. Okay, the relation between the features are not linear. May not be linear, or sometimes it may be linear, but it has to find out the relation between all the features. This is a first step towards the criterion of learning representation whose elements are statically independent. To achieve full independence, a representation learning algorithm must also remove the nonlinear relationships between the variables. Okay, variables in the sense the columns. We talk about the columns. Then the steps in principal component analysis. In the first step, we have to standardize the data. Standardize means all the data in all columns should be standardized. Standardizing means the mean of the data should be 0 and the variance of the data in all the columns should be 1. Okay, that is standardization. That means the data may be in different scales. Okay, something in rupees or something in kilometers and something in meters or something in dollars. Okay, so that all those data, the values may be varying. Some data may be ranging from, in one column you have the data ranging from 0 to 1, and in another column you have data ranging from minus 1000 to plus 1000. So there is a variance is very large between the data in different columns. So it has to be standardized first. That means for all the columns, the data should be, the mean of the data should be 0 and its variance should be 1. And in the second step, after standardizing, we have to compute the covariance matrix of dimensions. Okay, covariance. Next, we have to find out the covariance matrix. Then third, obtain the agent vectors and agent values from the covariance matrix. We have to find out the agent vectors and agent values. They are much important in this principal component analysis. That means, suppose we have 1,000 columns and I want to reduce it into 800, for example. So I have to find out which are the most important 800 columns. Okay, out of these 1,000 columns, which are the most relevant 800 columns. So in order to find out that, we use this agent vectors. Actually, agent vectors will tell you which are the important vectors, important 800 columns in your data set. Okay, and this agent vector will be, it will give you the direction or it will give you the dimension, and the agent value will give you how much scaling should be done to these data. Okay, so that means all the data in the range with the variance 1. Okay, all the data has variance 1, so its magnitude should be varying. We have to resemble the original data. So from 1, variance 1 to we have to reproduce the original data. In order to reproduce the original data, we use this agent values. Okay, and sort the agent values in descending order and choose the top k agent vectors that correspond to the k largest agent values. So k will become the number of dimensions of the new feature subspace, that is k is less than or equal to d, and where d is the number of original dimensions. So we assume that d is equal to 1,000 and k is equal to 800. So you find out the agent vectors and agent values and sort the agent values and vectors, agent vectors. Find out, take the largest 800 agent vectors. So that will be your new data set. Okay, construct the projection matrix W from the selected K agent vectors. So we take the projections. We are not actually cutting down the other 200 columns. Instead, we are taking a projection of those 200 columns to the remaining 800 vectors. Okay, 800 space. So that is projection. That means we have to get the effect of that. Cutting down 200. So to explain this, I can show you a graph like this. Okay, so suppose you have some data points. So this is x and this is your y, and you have data points here, and as you know, this is a two-dimensional space. It's a 2D data. Okay, it's a two-dimensional. That means it has x and y dimensions, so it is 2D. And if suppose I want to convert these data points, okay, so I have these many points here. So if I take it in a table format, I have two columns, x and y columns I have. Okay, and these are the coordinate values of if suppose this is 1 2. Okay, so if for this point it is 1 2, so it is 1 2, like that. For every point there will be coordinate values. Okay, I want to cut down this 2D to one dimensional. Okay, one dimensional. Okay, this is 2D or this is 2D. I want to convert it into one dimension. So you know that one dimension is actually, it's a line. It should be a line. So one method, what happens if you cut down the y as such? If you cut down y as such, you will get, how do you get the points? Like you get the projection of each point to your x-axis, and this will be your data set. Okay, this will be your data set. Like this. So when you project it to x-axis, you will get in one dimension, or in other words, so in this case what happens is you will not get the effect of y. You totally ignoring the effect of y in this data set. That is the property explained by y, that is we are losing it. Okay, so it is not recommended. And in the reverse thing, if you cut x-axis, Okay, if you cut this column, first column, and you get the projection to y. Okay, so you can represent in y axis, okay, like this. So your data will be these things, okay, the projections onto y. So this will be your one-dimensional representation of your data, or in other words, if you are choosing x-axis, this will be your one-dimensional representation of the data. But actually in both these cases you are losing the effect of one or the other. If you cutting down y, you lose the effects of y. Okay, you cannot this x-axis cannot actually represent the properties of y as well. So we are losing information actually. When you cut down blindly like this, we are losing information. So what to do? Suppose you are choosing a line like this. Okay, if you are choosing a line like this, you will get the effect of x and y as well, right? You will get the effect of x and you will get the effect of y, but still it is in one dimension. It's a line. Okay, so you can project this point to this line, you can project this point to this line, and like that. Okay, so at some extent you will get an effect of both x and y without losing the effects of x and y completely. We can reduce it to one dimensional. So that is actually happening here. So you find the eigenvector, and if the eigenvector, your eigenvector vector's direction, okay, it should actually passing through the origin, okay, passing through the origin, okay. So the eigenvector direction is this, okay. The eigenvector direction is this, not in x direction or not in y direction. Eigenvector is in this direction, and you have to find out the projection to that direction. Okay, you have to find the projection in that selected k eigenvector. So here we have selected only one eigenvector, so it is one, since it is one dimensional, and you have to reduce your data into that line, okay, or into that dimension. Okay, if it is one dimension, you have to reduce it to one dimension, or if it is two dimension, you have to reduce. That means if you have two eigenvectors, you have to reduce it to two dimension, like that. So that is the importance of projection. Projection will give you a new representation for your data without losing much information. They transform the original dataset X via W to obtain the new k-dimensional feature space. Okay, so this will be the points on this line are the new datasets, and that is PC all about. And let us see. So it's a representation. It is in 3D, from 3D to 2D conversion we have shown here. Okay, this is 3D and 2D, and we have find out the principal components or the eigenvectors. So this is PC1 and PC2. These are the two eigenvectors we found out, and using these eigenvectors we map our data. So this will be this axis will be our eigenvector 2, and this axis is our eigenvector 1. So from 3D we converted it to 2D. So that is one example for dimensionality reduction and principal component analysis. And in the first step we do the standardization. Then when there are different scales used for the measurement of the values, for example, you have height values, okay, height. In some countries it is in centimeter or in meters or in feet. Okay, it varies. Okay, so this may be this will be large values. It may be in hundreds. Okay, in hundreds, these will be in hundreds, and this will be in 1 point, 2 point, like that, and this will be in 5 feet, 6 feet, like that. Okay, so you can see that the range, it ranges differently. Okay, so if it is these values will be in different ranges, so in different scale. So we have to first standardize all these things. So then it is advisable to do the standardization to bring all the feature space with the mean value 0 and variance 1. That is the condition. And this is the equation we use for standardization. Standardized value of xi is equal to xi minus mean of x divided by standard deviation of x. So it's a mathematical term. Then that is standardization. So you remember this thing, this is our aim by standardizing. Variance should be 1 and mean is 0. Then we have to find out the eigenvectors. So for that we should know the covariance matrix. First we have to find out the covariance matrix, and from covariance matrix we have to calculate the eigenvectors and eigenvalues. We call it as agent decomposition overall. The eigenvectors and eigenvalues of a covariance matrix represent the core of PCA. PCA is principal component, and this eigenvectors are actually the principal components. The eigenvectors or the principal components determine the direction of the new feature space. It gives you the direction. Just as I said in this example, it is not x direction or it is not y direction, but we take this direction. So that is the eigenvector direction. And the eigenvalues determine their magnitude. So eigenvector is actually a unit matrix, a unit vector, and the eigenvalue will give you the magnitude we have to project. Then to get the eigenvalues and eigenvectors, we need to compute the covariance matrix. So we have to compute the covariance matrix, and from that we have to calculate the eigenvalues and eigenvectors. Okay, it's a long process. Okay, that is about the second and third step. And then we have to find out the principal component. Once we have got all the eigenvectors and eigenvalues, from that we can choose the principal components. So the typical goal of PCA is to reduce dimensionality of the original feature space by projecting it onto a smaller subspace. Okay, that means if we have a 3D data, we have to convert it into 2D maybe. Or if we have a 1000-dimensional data, you maybe want to convert it into 800-dimensional data. Anyway, you have to reduce the dimensionality by projecting onto smaller dimensional space. Okay, smaller dimension from 1000 to 800 or 3 to 2 or 4 to 2 or 4 to 1, like that. Okay, where the eigenvectors will form the axis. So when you do the reduction, the axis actually are the eigenvectors. And however, the eigenvectors only define directions of the new axis since they have all the same unit length. Okay, eigenvectors are unit vectors. Sort the eigenvalues in descending order. Okay, that's how we are going to find out the principal components. Eigenvalues in descending order, and then choose the top k features concerning the top k eigenvalues. Okay. So we choose the columns that are actually representing the top 8, top k eigenvalues. Okay. And from that, we choose the principal components. That means the highest eigenvalues we will choose, highest eigenvalues. Highest k eigenvalues we will choose, and its corresponding directions, that is eigenvectors. And from this, the principal component, we have taken the principal component, and suppose we have taken the 800 vectors or the 2 eigenvectors we have taken. And next step is we have to reduce this 3 dimension to 2 dimension. Okay, and this direction of this 2 dimension is the dimension, the direction of the eigenvectors. So that's what we are going to do. In the next step is projection. Construct the projection matrix W from the selected k eigenvectors. So these projections can be represented in the form of a matrix, that is W. Projection matrix will be used to transform the data. Okay, it's not data onto the new feature space, or we say newly transformed data set with reduced dimensions. It is a matrix of matrix of our concatenated top k eigenvectors, reducing a 4-dimensional feature space to 2-dimensional features 2D space. That is an example. Okay, we can we have to reduce to 4D to 2D. So what happens is we list out all the eigenvectors. Okay, eigenvector 1, 2, 3 like that in their suppose it has 3 eigenvectors or 4 eigenvectors. So we choose the top 2. Okay, that means we want to reduce to 2. So we choose the top 2. So if you want to reduce to 3-dimensional, we have to choose the top 3 in that way. And next is the projection. So we choose the dimensions and the directions we have selected. Okay, so we selected the eigenvectors and the directions we got. And now what we have to do is, from this 4-dimensional, I have to map it into this 2-dimension. So how do we map it? That is called as projection. So we projected the data from this to this dimension. So that's an example for the projections. So suppose you have a data in 3D space. You have an object in 3D space. This is a cube. Okay, this is a cube, and when you project it into a 2D space, you will get a square. Okay, suppose you are projecting from this direction. Projecting from this direction, what you will get? You will get a square in 2D space. Okay. Or if you project it in from this direction or in this from any of the sides, if you project it, you will get a square shape as a projection in 2-dimensional space. And when you project this one into a one dimension, it will be a line. Okay, like that. If you project it from this direction or this direction or this direction, in whatever direction, when you project it to one dimension, it will be a line. And when you project it to 0 dimension, it will be a point, single point. Okay, that's how it looks. So you can see that when you project from 3D to 2D, you lose some kind of information. Like if you project it like this, you lose the information. Suppose you are projecting in this direction, you will get this measurement and you will get this measurement. So that has been projected over here. This measurement you will get, but you will lose this height information. Okay, so you will lose the site information. So in original projections, using the W matrix, what we want to do is we have to preserve some of this information instead of cutting down the entire height information or one dimension information. We try to preserve these data, these information in some other form. Okay. So I haven't included much examples in projection. So you can take the same example as I said here in this one. Okay. So this is from 2D to 1D projection we are taking. It's an example. Then that is about principal component analysis, and the next algorithm is K-means clustering. So it's a clustering. KMeans clustering is one of the simplest and popular unsupervised machine learning algorithm. The objective of K-means is simple: group similar data points together and discover the underlying patterns. That is the main objective of the K-means clustering. So we have to group the similar data and find out the patterns. To achieve this objective, K-means look for a fixed number of clusters in the data sets. So this in K-means, K is the number of clusters we are looking for. Actually, the system does not know how many clusters are there in the system. Suppose you have entered a set of images. Okay, so you ask the system to find out the categories. So when you insert or when you give input to the system, suppose you are inserting some 10,000 images to the system, you are giving it as input. So out of this 10,000 images, the system actually does not know how many kind of images are there, whether it is images of flowers, fruits, animals, like that. It may be, there may be different categories. So how many categories are there, that itself is unknown. So this K is actually representing the number of categories in the, or the clusters in the data set. So to achieve this object, K means look for a fixed number of K. It looks for a fixed number of K of clusters in the dataset. So it has to discover the value of K. To cluster, a cluster refers to a collection of data points aggregated together because of certain similarities. So in clustering, we have to group the data based on their similarities. Suppose if you have if you have images of flowers, so all the flowers have some similarity, and the animals have some similarity in their structure and all. So based on the similarities, they are grouping the elements or grouping the data. So this term is important, the similarities. Define a target number K, which refers to the number of centroids you need in the dataset. A centroid is the imaginary or real location representing the center of the cluster. So we have to define this number K that refers to the center of the cluster. Okay. Every data point is allocated to each of the clusters through reducing the in-cluster sum of squares. Okay, so we find out or we organize the data under different clusters based on the sum of squares by reducing the sum of squares. Then in other words, the K-means algorithm identifies K number of centroids and then allocates every data point to the nearest cluster while keeping the centroid as small as possible. Okay, so that's how we form the clusters. First of all, we have to identify the K number of centroids. The centroids means the center point of all the clusters, and then allocates every data point to the nearest cluster. We have to find out which this data is belonging to that cluster or this cluster. The means in the K-means refers to the average of the data, that is finding the centroid. Then how the K-means algorithm works. So to process the learning data, the K-means algorithm in data mining starts with the first group of randomly selected centroids, which are used as the beginning points for every cluster, and then performs iterative or repetitive calculations to optimize the position of the centroids. So we in order to find out the centroid, first we start with some random positions, and then we make it accurate through several iterations. It halts creating and optimizing the clusters when we stop this optimization, the centroid have stabilized. That means the centroids are not changing much. It is the position of the centroid is stabilized, or it is stable. There is no change in their values because the clustering has been successful. That is the one point when we stop the iterations. Or the other condition is the defined number of iterations has been achieved. So we may be setting 1000 iterations. So after 1000 iterations, we will stop the execution. So these are the two possibilities to stop the iterations. Either we reach the maximum iterations, or the centroids, we have reached a stabilized center. Okay. So the steps involved in K-means algorithm, the first step, we need to provide the number of clusters K that need to be generated by this algorithm. So we should give the value of K as an input to the algorithm. The system cannot actually, they don't know what is the number of K. Then second step, choose k data points at random and assign each to a cluster. Briefly, and categorize the data based on the number of data points. Okay. So choose k data points at random and assign each to a cluster. So we take a set of data sets and assign to each cluster. The cluster centroids will now be computed. Okay, the centroids will be computed again. Iterate the steps below until we find the ideal centroid, which is the assigning of data points to cluster that do not vary. So the first step is the sum of squared distance between the data points and the centroid would be calculated first. So sum of squared distance between data points and with the centroids, between data points and the centroids has to be checked. So it should be close to each other. At this point, we need to allocate each data point to the cluster that is closest to the others. That means the other centroid. So if if a particular data point is closest to one centroid, we have to allocate that data point to that cluster. Okay, like that. So this step has to be repeated continuously. And finally, compute the centroids for the clusters by averaging all of the clusters data points. Okay, so like this, if suppose you have you have find out some clusters initially. Suppose it is 3 means k is equal to 3. Suppose, okay. So if you get a if you have you take a data point and you check the distance between this cluster and this cluster, the centroid and the centroid, and which one is smaller, this distance is smaller, so you make this data point belonging to this cluster. And if you have another data point here, and when you take this distance is smaller, so you allocate this data to this cluster, like that. Okay, and after adding this data, you have to recalculate the centroid of this cluster. Also, you have to recalculate the centroid of this cluster and this also. So the centroid may be changing from this position to this position when you add the new data. So the centroid is changing to this one. And again, you have another data. You compare. This is the shortest distance. So you take this data to your this cluster, like that. So every time in every iteration you add the data to a particular cluster and you have to reset the centroid also. And at some point this centroid will remain at the same place after several iterations. So at that stage we can say that this is the actual centroid of this cluster and we have formed the cluster as well. So we can stop the iterations. Or in some cases, we cannot find a fixed position for the cluster centroid. It may be here at one point and it may be here at another point, like that. It may be varying like anything. So we will go for the maximum iterations, and when it expires, we will stop the execution. That too. So two conditions are there. So these 4 steps we have to repeat until we find an ideal centroid, or we are exhausted with the iterations. And its representation is like this. After that, we will reassign each data point to its new centroid. Okay, we shall repeat the procedure outlined before using a median line and the cluster. So it's like this. Okay, the centroid was here. This square shape is the centroid, and this is the centroid. So after adding each data, we change the centroid. The reassignment has occurred. We will repeat the previous step. So the thing, okay. So what happens is these two data based on the checking. Okay, this one. After assigning the new centroid, we compare the distance. This point to this centroid and this point to this centroid. So if it is smaller, we make this point as a this yellow cluster. Similarly, this point also is changed to yellow cluster. Okay, so after centroid, after the change in centroid, these data points, there may be some change in the clusters of these data points. So this data, it is actually labeled as the clustered as yellow, but after the change in the centroid, when we recalculate, we find that this is belonging to the blue clusters. Repeat the procedure outlined above for determining the center of gravity of the centroid as shown below. So we find out the centroid, the original position of the centroid, or we find a new position for the centroid. So the centroid has been changed like this. Okay. And group the points depending on their distance from the median line. So this is the median line, and we group the data points based on the median line. Okay, so it's grouped like this, and final cluster will be like this. Okay, so we clustered the data into different clusters. Okay, so this is K-means clustering. So here we have two clusters. So this is all about the unsupervised algorithm. So in this we have seen only two algorithms. One is principal component analysis, and the other one is K-means clustering. So these two are the things we have seen. So this is